Hello everyone, I'm J Wildberger and welcome to this famous math problem where I'm going to try to show you how to construct the true complex numbers. This is going to be a novel point of view that's going to be very different from the standard approach in textbooks and in courses, and it's going to be more general and powerful and ultimately will open up lots of new directions for you. So there's actually quite a lot of novelty in my proposal of how to introduce this very important concept. So the usual story, which is found in texts and courses around the world, is that the complex numbers are a set created from real numbers. It's a quadratic extension of the real number. So the objects are things of the form a plus bi, where a and b are supposedly real numbers. These things which don't really exist, that you can't really write out properly, but anyway, so it's a kind of an imaginary world. And this I is, well, some kind of new number, which is characterized by this defining property that I squared equals minus 1. And then there are two operations of addition and multiplication. Addition is essentially component-wise. Multiplication is more subtle and has the form a plus bi times c plus di is ac minus bd plus ad plus bci. Okay, and then we picture complex numbers in a two-dimensional fashion with an x-coordinate and a y-coordinate. So this, for example, would be the complex number 2 plus I. And this new axis here is kind of a new axis involving the complex number I. They call it the imaginary axis. And then in terms of this, we define some auxiliary concepts like the complex conjugation. A plus bi conjugate is a minus bi. That's like the reflection of this complex number in the x-axis. The modulus of this complex number is denoted with these absolute value signs. So the modulus of a plus bi is the real number square root of a squared plus b squared. So it involves crucially a square root, which is an infinite operation in general, not always, but most of the time, an infinite operation that you can't actually complete. So we usually invoke some symbolics to try to represent this thing that we can't actually write down. Also, closely associated with that is the idea of an angle or an argument. So that's this supposed angle that you get by looking at the x-axis and the ray from the origin. And in terms of the entries a and b forming the complex number, one way of expressing it is as tan inverse of b over a. So you need some transcendental functions here to try to make sense of this. So typically, even for something like 2 plus I, you can't actually really compute the modulus or the argument, but nevertheless, these are kind of foundational building blocks for the usual theory. We are going to be presenting a very different approach because I want everything to be completely algebraic and on the page, okay? So that everything is there in its entirety and we don't have any computations going off the page or off the universe. Okay, so we are going to be showing you a brand new and exciting and bigger story for complex numbers. So complex numbers have an important history going back to around 16th century mathematics. Actually, the origins really are with work in the direction of solving cubic equations. You might think it's quadratic equations, but no, it's actually the cubic equations where the complex numbers really first took hold. That was with the work of Tartaglia, Del Ferro, Cardano. Certain formulas involving a solution to a general cubic equation involve these sort of curious combinations that sometimes necessitated kind of introducing these complex numbers, these square roots of minus quantities, for example. Later on, they were studied in various different contexts by many great mathematicians. Euler, Lagrange, Gauss, Argonne, de Moivre also made contributions, and many other people also. But there was always this sense of, what exactly are these things? We are broadening our arithmetic in some fashion or another, but is it exactly safe? Do we know for sure that these things really make sense or exist in some sense? You see, there's an issue that if you have a number system that you are very familiar with and you trust, and then someone comes along and says, let's add something else with some magical property. how do you know that that magical property is actually not perhaps subtly inconsistent with the framework that you already have? In other words, maybe imposing this additional property actually generates a contradiction far down the road. How do you guarantee that that's not going to happen? That's a subtle question, which I think maybe wasn't put so directly, but it really is part of the story. How do we know that this framework really works? But certainly there were lots of very useful applications of this theory. Euler and others introduced the idea of complex functions, ultimately leading to the grand theory of Cauchy. The subject had important connections with group theory, also connections with hyperbolic geometry, work of Klein and Poincaré and others, and then differential equations. And sort of by the end of the 19th century, complex numbers had woven their way into the fabric of many different areas of mathematics. After the fundamental theorem of algebra was more or less put on a firm footing, that took quite some time, and as you know, I still do not really believe this, so I think I'm a skeptic about this. But anyway, after that, there were then connections also with number theory, with algebraic and analytic number theory, and the more modern treatment of Galois theory, at least with some of the versions of Galois theory. Okay, so what we want to do is we want to reposition and enlarge the subject. So the problem is how to construct the true complex numbers. And I'm going to show you how to do that, as best I know. And it's going to involve us going in a lot of different directions from the standard story. So there will be a lot of interesting things to touch base with. And while we're doing it, I'm going to be a little bit bold and introduce some novel, but I think important new kinds of notational features that's going to ultimately help us in understanding this numerical system. Now, in the usual treatment, complex numbers are thought of as a field, which is, informally at least, a kind of arena for doing arithmetic, which mimics or generalizes the idea of the rational numbers. Okay, now field theory has quite some different aspects, and it's really useful, and I think very important, to distinguish between finite fields and the non-finite or unbounded fields. Okay, that's a very important distinction to make in lots of different branches of algebra, actually. And the way I want to think about it is that we have to treat these quite differently. So the kinds of arguments, the kinds of definitions that we make in the finite field story are not going to so easily or immediately transfer to unbounded fields. We'll have to think a little bit differently. But still, we are aiming towards the same kind of overall structure. And that's encoded rather briefly in this map of the main features that we want fields to have, whether they're finite fields or unbounded fields. So the key features of this theory are that there are two binary operations, addition and multiplication. There is also a unary operation, which is meaning that you input one thing and you get out something. So this is the operation of taking multiplicative inverses. So these are sort of entry things that you need an operation of addition, you need an operation of multiplication, and you need a unary operation of multiplicative inverses. Then in addition, there are some special elements. There are three special elements that play an important role in the theory of fields. And we're going to be rather novel here. I'm going to give them, two of them, the standard names, 0 and 1. The third one, I want to introduce a novel notation for -1. I do not want to write -1 with a minus sign followed by a 1. There's really good reasons to let go of that particular way of representing negative quantities. The bar over the 1 is going to be what I'm going to propose as an alternative way of expressing negation. So these three things are 0, 1, and -1. You could also say 1 bar. So the usual story would be 0, 1, and minus 1, okay? So let's just give a chance, okay? Let's just have a look at that. It has some interesting, pleasant features. And what do we want about this setup? Well, crucially, there are these commutative, associative, and distributive laws that these operations satisfy. So there's various requirements that are necessary. So although the entire setup is different in the finite and the unbounded cases, we still want these features to ultimately be corresponding. Now, one of the longtime viewers of my channel, Peter Ossadar, is a high school teacher in Canada, and he has often expressed the strong view that, in his opinion, arithmetic is best founded on a basis of finite fields, that finite fields should be primary instead of, say, the rational numbers or some other unbounded or infinite field. And actually, I have a lot of sympathy for this point of view. And increasingly, I think as we move into the 21st century, Peter's understanding here is going to become more and more important. We are going to be more and more thinking that, actually maybe ultimately the finite fields are really ultimately more important. So this is a possibility that we have to keep in mind. And certainly as we're moving towards establishing complex numbers, this is a good way of starting because the finite field situation is demonstrably simpler to deal with than the unbounded case. So let's start there. Let me give you an example of a finite field so you can see what it looks like. So here is a finite field. Its name might be F7. It has 7 elements. And here are the 7 elements, rather written in an unusual form. Remember that this 3 bar is really the same as minus 3. So we can read this as minus 3, minus 2, minus 1, 0, 1, 2, 3. Those are the 7 elements in this field. So what do we require to make a field? Well, we need an addition operation, and we need a multiplication operation, and we need a multiplicative inverse operation. So let's have a look at that. So first, the addition. Here is the addition table that tells you how to add any two of these 7 elements. So for example, let's say you want to add 2 plus minus 3. 2 plus minus 3. You look here, you see that's minus 1. Minus 1 plus 1 is 0. Minus 2 plus minus 2, well, usually that would be minus 4, but that's the same as 3. Now, those of you who have done a little bit of number theory will know about modular arithmetic. What we're really doing here is modular arithmetic, mod the prime 7. So basically, we're setting 7 equal to 0 so that 4 plus 3 is 0. And that means that 4 is like the same as minus 3. Okay? So instead of writing 4, we write minus 3, keeping the actual numbers that we're using in a tighter range around our central value of 0. There's the addition operation. Here is the multiplication operation, which is also multiplication mod 7. So for example, 2 times 3, that ordinarily that would be 6, but 6 is congruent to minus 1. So there's a minus 1 here. 2 times 3 is minus 1. That's the multiplication. And here is the unary operation of inverses, which actually can be deduced from this thing. So the multiplicative inverse is defined by the property that the inverse of an element is the unique element whose product with the original element is equal to 1. So if we want to find, say, the inverse of 2 bar, there's 2 bar or minus 2, we have to look along here and ask, what do we have to multiply 2 bar by to get 1? Okay, and we see that there's only one 1. There's exactly one 1 in this row. We have to multiply 2 bar by 3. So that means that the inverse of 2 bar or minus 2 is 3. The inverse of minus 3 is 2. The inverse of minus 1 is itself, because minus 1 times minus 1 is 1. 0, crucially, does not have an inverse. All the others do. And the inverse of 1 is 1, the inverse of 2 is minus 3, the inverse of 3 is minus 2. And one way, at least, of visualizing this is to arrange the elements in kind of a circle, okay, one after the other, and then closing back up again. It doesn't actually have to be a regular 7-gon, just range points on a circle, 0, 1, 2, 3, minus 3, minus 2, minus 1, corresponding to 1, 2, 3, 4, 5, 6 in the usual story. So this way of representing the elements means that we don't have to use anything other than 1, 2, and 3 in this particular field. We don't have to use 4, 5, or 6. So it shortens things and actually makes tables like this actually ultimately perhaps simpler to write down. You may have a look at these tables and observe various symmetries that are quite pleasant about these tables. Now, let me say a little bit about, so in summary, to specify this finite field, what do we really need? What you need is for your computer to have this table loaded, and your computer to have this table loaded, and your computer to have this table loaded. It's actually not necessary to have a prior understanding of what the rule is that are represented by these things. So in other words, we can think of this data as being self-contained without any prior explanation required. So we don't have to say, oh, we're doing arithmetic mod 7. We just say, look, here's the addition table, there's the multiplication table, there's the multiplicative inverse table, and the computer can check, if necessary, by going through all the cases, that the various laws of arithmetic that we want to have satisfied are actually happening. So that's quite interesting that there's a kind of a self-standing independence of this data on any underlying theory. It's just the fact that we have these 3 lookup tables on our hard drive, and that, as long as the tables satisfy the right criterion, gives us a field. So what are these criterion that these operations have to satisfy? All right, so a field has to satisfy certain properties, and here they are. First of all, commutative laws. The operations of addition and multiplication have to be commutative. Doesn't matter which order you do things in. So a plus b is the same as b plus a, and a times b is the same as b times a. They should also, both of them, be associative. So if you have 3 elements, a plus b plus c is the same as a plus b plus c. And also for multiplication, a times b times c is the same as a times b times c. So we don't need to actually have these brackets when we're doing the same operations with a number of different elements. And then the distributive law connects the addition and the multiplication so that a times b plus c is a times b plus a times c. And we agree that we can dispense with the brackets here so that this can be just more concretely represented this way, with the understanding that you do the multiplication first. So the multiplication takes precedence over the addition. Now we have these 3 special elements, 0, 1, and 1 bar, or minus 1, and they have some properties. So 0, which is arguably the most important element, it's right in the middle, 0 plus a is a for any element a, and 0 times a is 0 for any element a. 1 is the multiplicative identity. So 0 is an additive identity. 1 is the multiplicative identity. So 1 times a is a. And what about minus 1? Its role is determined by this equation, that 1 plus minus 1, or 1 bar, equals 0. Okay, so in addition, there is one more property, which is maybe the most subtle one, which is the inverse property, which says that if a is not equal to 0, then there's some other element, well, it might be it's actually equal to a, but there is an element called a inverse, which was given by that unary operation of inverses, that has the property that a times a inverse is equal to 1. Okay, so those are the laws. And then we can prove various consequences of these laws. And these are good exercises for you to do if you haven't seen them before. The first is that actually these three elements, 0, 1, and -1, or 1 bar, are actually unique. So in other words, there's no two elements masquerading as 0 that have the same properties that 0 does. There's a single 1, there's a single -1. You can prove that -1 times -1 is 1. And then you can use the existing objects to introduce some new things. So you can define minus a, or a bar, to be -1 times a. And then you can introduce subtraction as a kind of a secondary operation. A minus b is by definition a plus minus b, or b bar. So the subtraction becomes dependent on the addition. The addition is primary, subtraction is secondary, together with this bar operation, which is really encoded in the multiplication by the -1, or the 1 bar. And you can also introduce a complementary secondary operation for multiplication, namely division. A divided by b is a times b inverse. However, that requires b to not be equal to 0, because our inverse law requires that the element that has an inverse has to be non-zero. Okay, so once you've done this, then you actually have an arithmetical setup that actually has 4 operations: addition, multiplication, they're the primary ones, and then these secondary ones of subtraction and division. So it is quite complicated, okay, but it's motivated by the fact that the rational numbers have these properties, and importantly also that the finite fields, at least for example the finite field F7 that I showed you, which you get by looking at arithmetic mod 7, that it has these properties, and you can check that these properties are all satisfied. So now let me outline the path towards our new understanding of complex numbers, rather more generally, rather a bigger picture than usual. So the first thing that we do is we start with the field F. That's sort of the starting point. Now, for many things in geometry, the rational numbers are a really good starting point. So that's certainly a good candidate. However, finite fields are also an excellent starting point because they're so specific, and your computer could get complete control over the arithmetic of these things. Real numbers, much less so, because the arithmetic of real numbers is largely vacuous. I remind you, I keep asking people, what is pi plus e plus square root of 2? That's an example of real number arithmetic, which, curiously, no one can seem to answer. Okay, so we don't want to really be thinking about real numbers, but in principle, you just start with a field. So if you really are addicted to the real numbers, start with the real numbers then. Okay, but we do need to make a distinction that the corresponding theory that we're building is going to have a separation between whether we're starting with a finite field or an unbounded field. But I've told you that the finite field is much more concrete and specific, and it can be entirely put on your computer. You get the whole thing there. Not so with an unbounded field, so you have to do things differently to go from, this concrete situation to this other situation. But still, at least in principle, there's a path forward. So you've got a field. Now what do? Now you have to choose a geometry. And there are 3 nice choices of geometry here. One is Euclidean, and the other 2 are relativistic. Okay, so we're touching base with something which I call chromogeometry, which is a beautiful 3-fold symmetry in planar geometry, which I hope you've watched some of my videos on. It's a wonderful topic. But in any case, there are these 3 geometries: blue, red, and green, and I will explain things shortly, but what their role is. But the point is that what we're doing has really these 3 different aspects. You can go in the blue or the red or the green direction, and you get parallel but sort of different theories. And then the crucial thing is we have to construct a certain algebra. And I'm going to call it a quadratic inverse algebra, and I will explain what that means at some point. And so the name C sub b of f, that's the blue one, C sub r of f, that's the red one, C sub g of f, that's the green one. Probably the usual story is best captured by this blue one. That's like the Euclidean one, that's sort of the garden variety one that you're most likely familiar with. But I want you to appreciate that there are these two relativistic sisters or cousins, okay, that are ultimately every bit as good as the Euclidean one and equally important in lots of other applications. Okay, so it's good to have an orientation right from the beginning, appreciating that there's this threefold symmetry that we can go down. And how do we do this? How do we get this algebra just starting from the field? Well, what we have to do is we have to use some linear algebra. And this is the reason really why this treatment was not understood in earlier times and why 17th, 16th, 17th, 18th, and even 19th century mathematicians struggled with understanding the real role, the true role of complex numbers. It's because linear algebra was not sufficiently developed. Linear algebra is very much a late 19th century and particularly a 20th century development. Okay? And the attendant algebra of 2 by 2 matrices is going to play a central role for us. So we're working over a field F. We're looking at 2 by 2 matrices, arrays of the form A, B, C, D, where these entries here are just elements in the field. That is the arithmetical framework in which all of these complex number systems live. And this is ultimately the most powerful way of bringing them into being in the first place, where you see right off the bat what is really going on. Now, if your linear algebra is not quite up to speed, I suggest that you have a look at my Wild and Alge series of YouTube videos, which I think will give you a lot of background here for this. Okay, but we're only talking about 2 by 2 the case here, so it's relatively simple. So here, specifically, concretely, are these three algebras that we are going to be looking at. First of all, the blue one. Okay, we're going to be looking at matrices of this particular form. A, B, minus BA. Remember, this bar is like a minus. Okay, I'll say minus just to remind you about this convention. So A, B, minus BA. And using a bit of matrix arithmetic, the way we combine matrices, the way we multiply a matrix by a scalar, this can be written as A times the identity matrix, 1, 0, 0, 1, plus B times this matrix 0, 1, minus 1, 0. So that's the Euclidean version. And then there are these two relativistic ones, the red one and the green one. The red one is a lot like this one, except that there's no minus b here. There's just a b. So we're looking at matrices of the form A, B, B, A, and that's A times the identity plus B times this 2 by 2 matrix. And the green ones are just diagonal entries of the form A plus B, 0, 0, A plus minus B. Now we could rewrite this as A minus B, but I prefer not to because I prefer to stick with our fundamental operations, which are addition and multiplication. Those are the ones that are encoded on our computer, right? We can just look them up. Okay. And this can be rewritten as A times the identity plus B times now this matrix 1, 0, 0, minus 1. Now, beautifully, each of these is a two-dimensional subalgebra of the 2 by 2 matrices. What does that mean? It means that each one of them is closed under addition, under scalar multiplication, scalar meaning elements in the field, and multiplication. So if you take any two matrices of this form and you add them, you can get another one of this form. You take any two of them, you multiply them, you can get another one of this form. So this is closed two-dimensional subalgebra. This is a closed two-dimensional subalgebra. This is a closed two-dimensional subalgebra. But crucially, they are all commutative. Okay, so usually when we go from elements in a field to matrices, we have to deal with this complexity that matrix multiplication is non-commutative. We have to worry about the order of matrix multiplication. A times B is not necessarily the same as B times A for general matrices, even for general 2x2 matrices. But in each of these cases, if we restrict our attention sufficiently, then in these little subalgebras, everything is still commutative. Addition is always commutative, but matrix multiplication is also commutative. And that's what makes this so powerful, that now we have a way of thinking about extending our original arithmetic, starting with the field F, to this kind of two-dimensional version of F, which is still commutative with respect to multiplication. Now, an important aspect of the arithmetic of 2x2 matrices is that the original number system that you started with is sort of contained in this bigger algebra in terms of the diagonal matrices. Actually, the diagonal matrices with constant diagonal entry. In other words, if we associate to the element in our field A the matrix, which is 0 off the diagonal, and it's just A's down the diagonal, then that's an exact correspondence arithmetically. So the way you add or multiply two elements in the field over here corresponds exactly to the way you add or multiply them over on the matrix side. So we can think about our field F as sort of being inside our algebra of 2x2 matrices. It's not exactly, but it's a convenient representation. All right, so this then gives us a distinguished basis of this space of 2x2 matrices. First of all, the identity matrix, which is what we're getting here. We're taking A times the matrix 1, 0, 0, 1. Usually this is the matrix that's denoted with an I, but I don't want to do that. So let's call this rather just the matrix 1. Okay, so it's a little bit of an abusive notation. So this 1 will refer to this matrix in this context. And the other three 2x2 matrices that appeared in the blue, red, and green subalgebras that I described are I, J, and K. So I is 0, 1, minus 1, 0. J is 0, 1, 1, 0. And K is 1, 0, 0, minus 1. So if we agree to that, then these four matrices actually form a basis for the space of matrices 2x2. In other words, every matrix can be written as a unique combination, a linear combination of these four matrices. And then we have a description of these sort of complex numbers that we've introduced. The blue complex numbers, C sub B of F, are things of the form A times this matrix plus B times this matrix. And we'll allow ourselves to just write that as A plus BI. Now we see what the role of I is. I is just representing this particular 2x2 matrix. And the crucial property that I squared is equal to minus 1 is just what you get when you take this matrix and you square it in the world of 2x2 matrices. You square this matrix, I hope you can all do that. You're going to get the negative of this thing. This is 1, so you're going to get minus 1. All right? So this is the linear algebra way of describing what the imaginary number, this mystical, strange creature I is. It's just a particular 2x2 matrix, very simple, entry 0, 1, minus 1, 0. That is I. But then we can do the same thing for J. There's J, and so the red complex numbers over F are things of the form A times 1 plus B times J, which we just write as A plus BJ. And we ask, what is J squared? You square this one, you get the identity matrix again. So J squared equals 1. Not minus 1, 1. And the green case, you take this matrix and you take a combination A times this matrix plus B times this one. You can rewrite that as A plus BK, and then K squared, this one here, squared is equal to 1, just the same as J squared is. So now we have a nice threefold symmetry. We could have just done this all in the blue setting, but I think it's really important to have these three together at the same time so we're seeing them all together, because there's a beautiful kind of symmetry between these things and a parallel between the complex number theory that has been built up over centuries. In the Euclidean case, there's a parallel for that in the relativistic settings as well. And the connections between these things are very important. Okay, and have a lot of possible connections with relativistic geometries. Okay, so we've introduced quite a lot of new ideas. Okay, in my next video on this subject, I want to go further and with this framework that we've made here, I want to establish more of the theory of these complex number domains and investigate their properties further. And we're particularly interested in this interesting question is, when do we actually get a field out of all this? I mean, are these things fields? Well, the answer is sometimes, but not all the time. Okay, so we need to enlarge our idea of a reasonable number system for us to make explorations in. Hope you'll join me for that. I'm J Wildberger. Thanks for listening.